All right, this is the fourth and final video for Chapter 13 in Julia Burgess' fifth edition of chemistry. So what we're going to talk about today is colligative properties. We've been talking about a few already. We've talked about vapor pressure. We've talked about freezing point depression, boiling point elevation. But the one we're going to talk about today is the most important, I believe, for especially the allied health majors, and that's osmotic pressure. So let's get right into it. I hope you'll spend the time to really understand osmotic pressure. It's so important when we talk about cell biology, when we talk about separations and so forth. Osmotic pressure becomes a really important component of that. So many chemical and biological processes depend on osmosis. It's the selective passage of solvent molecules through a porous membrane. So you have a membrane. For us, it's going to be, it could be an actually manufactured semi-permeable membrane. It could be a cell wall. It could be, you want something that you can see every day. It could be like a cucumber skin, which is really a cell wall too. But there's different applications to show osmosis. And so what happens is that the solvent, because it's smaller in size than the solute particles, it can pass freely between the membrane, and the solvent will move through the membrane from the dilute solution to the more concentrated one, trying to get both sides of the membrane to have the same concentration. So let's look at a picture of it just to give you an idea of what's going on here. So we have two containers, and you can see from the containers that let's see, I'm having a little bit of difficulty here. Okay, not sure what's going on. So we have these two containers, and you can see just by color that this one is more concentrated, this is dilute. And so what happens is the cell membrane, you have openings here. So that's what we mean by semi-permeable membrane. But only the solvent molecules or solvent atoms, either way you want to think of it, are small enough to go through these holes. The solute cannot go through the holes of the semi-permeable membrane. They're too large. So what happens is the solvent from the more dilute side will move through these holes, and that will keep happening until both solutions are the same concentration, or another way to say it is when the osmotic pressure is the same on both sides. So see, you notice what's going on here is as the dilute solution moves through, you notice that this decreases and the volume over here increases. So if you want to stop this dilution effect, you would apply a pressure to this container that would force the solute or the solvent from not transferring over. So you block off this so that the solvent cannot go through the membrane. So that's where we get the word osmotic pressure. It's the pressure required to stop the flow of the solvent through the semi-permeable membrane. So osmotic pressure, its symbol is pi, and pi is proportional to the molarity, and so osmotic pressure is equal to the molarity times R, the gas constant, times T, the temperature, the absolute temperature. It's got to be in Kelvin. So R is the gas constant, T is the absolute temperature, and M is the molarity. You need to memorize that equation. You'll have it memorized after you do the assignments. You'll get a good feel for this. So you've got really three variables here. You've got osmotic pressure, you've got molarity, and you have temperature. And most of the time, a reaction is going to occur at a constant temperature. So really, it comes down to molarity and the osmotic pressure. So two solutions that have the same osmotic pressure or equal concentrations, let's say that, they're said to be isotonic. So isotonic means iso means same. So same osmotic pressure, same concentrations, because we just saw that pi, the osmotic pressure, is equal to molarity times R times T. So if R and T are constant, then we see that pi is equal to molarity. And so when the concentration is the same on both sides, osmotic pressures are the same on both sides, we call that an isotonic solution. So that means that solvent is not going to be flowing in one particular direction, that it's balanced. They have the same concentrations. So we're not going to see the flow of solvent from dilute solution to concentrated solution. All right, this is a really important part, and some people cover this and some people don't. I think it lends itself to being covered, and the reason why is because we've been talking about, glucose, which is a molecule. We've been talking about ethylene glycol, which is a molecule. And we've stayed away from ionic compounds. And the reason why we stay away from ionic compounds that dissolve in water is that when calcium chloride dissolves in water, if we have 1 mole of calcium chloride, we're going to end up with 1 mole of calcium ions, and we're going to end up with 2 moles of chloride ions. So we get 3 moles of particles for every 1 mole of this formula. And so we have to take that into account. So if each one of these acts independently, it would be a full 3 moles of particles for every 1 mole of calcium chloride dissolved. So colligative properties depend only on the number of dissolved particles, not the type of the particle. So the Van 't Hoff factor, which is symboled by I here, is the actual number of particles in the solution after dissociation. Now notice I use the word dissociation. We talked about this in Chem 170, that an ionic compound is actually already ions even when it's a solid, and when you put it in water, all that happens is it dissociates. Each ion gets separated. That's different than a molecular compound like hydrogen chloride. When we bubble it through water, we ionize it. We form hydronium ion plus the chloride ion, and we form ions this way, but this is ionization, this is dissociation. So the Van 't Hoff factor is the number of particles in solution after dissociation divided by the number of formula units initially dissolved in the solution. Okay, so this is called a formula unit here, formula unit. So let's see this in action here. So that changes our equations. So our equations become the change in temperature when we do boiling point elevation, or the change in temperature when we do freezing point depression, is no longer just the constant times the molality like we saw before. Now we have the Van 't Hoff factor. The Van 't Hoff factor. Same thing with osmosis. It's not just molarity times gas constant times T. Now we have the Van 't Hoff factor. The number of particles after dissociation divided by the number of formula units. So this is a good slide. You may want to make a note of this because this is in a nutshell the equations that you need to know and be able to use for colligative properties. All right, so that's when we get into the talk about electrolytes. So when we talked about sugar and ethylene glycol, they're molecular compounds, but another way we classify that is sugars, alcohols, oils generally do not dissociate into ions, or they don't ionize into ions. So it is the electrolytes that give us more than one they give us more than one ion when they dissociate. So here, this is chloride, maybe this is sodium, and when they dissociate, we now have 2 particles for every 1 sodium chloride. So it says an ion pair is made up of 1 or more cations and 1 or more anions held together by electrostatic force, and when we place that in water, those become hydrated or undergo dissociation or solvation. There's different words for that mean pretty much the same thing, and we get more particles. More particles, that's what colligative properties are all about, is how many particles dissolve. So this next slide, this is where it gets a little technical. So normally when I'm teaching this class, and this is pretty much what we're going to do too, if you calculate the Van Hoff factors, these make sense, right? If you have iron 3 chloride, so that means iron's a 3 positive ion, and you have 3 chloride ions, and that makes this compound. So when this dissolves in water, and it should, and you go, how am I supposed to know that dissolves in water? Well, that's why you need to go back to chapter 3 or 4 and look at the solubility rules. So if it's been a while since you've looked at the solubility rules or you didn't memorize those, that comes into play here. So when you look at these substances, they do dissolve in water. Okay. And you can see the Van Hoff factor would be 4 divided for every one of these units. So it'd be 4 divided by 1, you get 4. That's what's calculated. And that's what I want you to focus on. This is what I want you to focus on, is the actual calculation. So magnesium chloride, when that dissociates, you would get a magnesium 2 positive ion, and you get 2 chloride ions. So the Van Hoff factor calculated would be 3, because that's what we get, 1 particle plus 2 more here. And then magnesium sulfate, you have to recognize that magnesium sulfate, first of all, you have to know what the chemical formula is, and then second of all, you have to know that dissociates into a magnesium 2 positive ion and a sulfate 2 negative ion, so you get 2 for the Van Hoff factor. Now, when we actually measure these, if they're not ideal, you don't get you get less than that, right? Notice on all these you get less, except for sucrose. And that makes sense because sucrose is not ionic. It's a molecule. It doesn't dissociate. It has an I of 1, and it's measured as 1. So that's what this slide's talking about, is that you can see all these electrolytes, all these ionic compounds, depending on how well they dissolve in water, depending on the interaction of the ions. We have the calculated Van Hoff factor, and we have the actual measured. And like I said, I'm more interested in the calculated. So you go, why do I need to know this again? Because when you salt the roads with sodium chloride, for every 1 formula of sodium chloride you put down, you're actually getting 2 particles. And those 2 particles, if this substance dissolves in water, we get 2 particles dissolved in water. That's going to lower the freezing point more effectively than sucrose, which is a 1-to-1 ratio. So yes, you can, in a pinch, you could possibly sprinkle sugar on your sidewalk to melt the snow. It'd be more costly. And the other thing is, sugar is probably not very soluble at freezing. But if the sugar was room temperature when you threw it out there, it would start to melt the ice. Now you go, why don't we do that? Well, sugar is a lot more expensive than sodium chloride. And then the other thing is sodium chloride, for every one you put out, you get 2 particles, so you're going to get a greater effect here. So the other thing you hear, like we had a really cold snap a few weeks ago, and so they said, well, we're going to use calcium chloride. Well, look at calcium chloride. When you dissolve this in water, and it's actually an exothermic process, so it warms up. That's why they call it hot melt. You actually get three particles: 1 calcium, 2 chloride. So you get 3 for the calculated Van't Hoff versus 2 for the sodium chloride. And this little bit of exothermic reaction allows us to work with calcium chloride at lower temperatures. So that's where we're going with this. I just want you to know the electrolytes, you got to decide that they do dissociate, and you got to know what they dissociate into. Like if you don't remember from Chem 170 that this is magnesium 2 positive, this is a polyatomic ion, then you're going to have problems. If you don't know that this dissociates into 2 particles, you're going to have some difficulty. Or if you don't know the name, that's another reason. So you may need to brush up on that. Like I said, I've got a naming video on my Professor of Chemistry channel that should be helpful. All right, so experimentally measured Van Hoff factors for sucrose. So what this is showing is as the concentration is less and less, the measured Van't Hoff factor is closer to what we would calculate. All right. So sodium chloride, when it's more concentrated, we should get 2, right? That's the calculated. It's 1.87. But as we get it more and more dilute solution, that means a lot more solvent, a lot less solute, we approach the calculated value. So that's what that's saying there. All right, let's look at one problem here. So again, stop your video. See if you can do this problem. If you can do this problem, you're in great shape. You understand the Van't Hoff, how to calculate Van't Hoff factor and so forth. So this is an osmotic pressure one. So right off the bat, you got to be thinking, oh, osmotic pressure, that's pi times the Van't Hoff factor times the molarity times the gas constant times T. All right. So then you need to have R memorized. My students had it memorized in Chem 170. And then the key here, this is one of the first mistakes I see, is convert that 25 degrees Celsius into Kelvin. So you're adding 273.15 plus 25 gives you that number there. All right. So stop there, try to work the problem out, and then we'll come back. All right, so you're back. So the first thing I would do is I just label this stuff, right? You'd come up here and you'd say, okay, osmotic pressure is 0.465 atmospheres. You know that the concentration is equal to 0.0100 molar. And you may want to break that out. You may want to say moles per liter. You know that the temperature is 298 Kelvin. You know what R is. And so the question is, what is I? What is the Van't Hoff factor? So you manipulate the equation. I equals mRT over osmotic pressure. Okay. Let's look at the next slide. These aren't that difficult. I think you can do this. It's just you got to know the terminology. Like I bet today you never heard of the Van't Hoff factor. And you may not have known about the dissociation of the ions and how that, maybe some of that's not quite clear. And again, if you don't, it's really back in the naming. It's back into chapter 2 in this book to kind of get the naming, and you can watch a video there. But so here we have the molarity of the ions. That's what they did. They calculated the molarity of the ions here, okay? And so pi over RT, 0.465 divided by RT. And what happens here is you can see that atmosphere cancels out. That Kelvin cancels out. This moles is in the quotient of a quotient, so that's the same thing as being up here in the numerator. And then you're going to take that and divide it, and then you got liters here. So that's the molarity of the concentration of the solution of the ions. And then you divide it by the original concentration of the formula unit, and you get 1.90. So it's almost 2. Let's go back. Let's look at that. All right. So, yeah, and that's what I should have said here. This is the molarity of the entire solution. Okay. This is the molarity of the entire formula unit. What we need to know is what's the molarity of the two particles, because potassium iodide breaks into these components. So the way we figure that out is the way they show it here on the next slide. Oops, not too far. And so based on that pressure, osmotic pressure, they're able to calculate the molarity of the potassium iodide. And notice it's about double. It's about double. It's not quite. If this broke apart 100% or dissociated 100%, then you would expect this to be 0.0200 molar in particles, all right, of potassium ions plus iodine ions. But we can't say that. We can't. That's what the calculated would be. But they're saying, hey, you can't do that. You're going to have to find what the molarity is of these ions, and then compare that to the molarity of the formula, which is just Ki, and then you'll determine the calculated, or you'll determine the actual Van't Hoff factor. And so it doesn't come out to be 2. It comes out to be, according to this problem, it comes out to be 1.9, 0.019, or 1.90, yeah. So it's pretty close to 2, but that's what it comes out to be. All right. Let's go on. So the next part is the colloids. So the colloids. So everything we've been talking about so far has been a solution. And so a colloid is it's heterogeneous. I mean, it's like milk. Milk is a colloid. So what you have is a solvent, and then you have particles that are large enough to cause scattering, and they may stay suspended, but they're in there. Now, that's the whole thing. A suspension, we say a suspension, the particles are so large that over time they will settle out down here. And we would call that a suspension. So if you scoop up some muddy water and you let it set long enough, the mud settles down, and then you'll have a solution above it, which is mostly the solvent. So the reason why these colloids are so important, again, biology, this is an important component of biology, and that's why we're going to talk about the colloids. So everything we've been talking about so far is a homogeneous mixture, but a colloid is not a homogeneous mixture. So that's what it says. Consider if we add fine sand to a beaker of water and stir. The sand particles are suspended at first, but gradually settle to the bottom of the beaker. And that is an example of a heterogeneous mixture. The other thing you know is that when you stir that sand up, it's cloudy. And if you try to pass a beam of light through it, you can see the beam traveling through it. Just like on a foggy night, you can see your car beams from your lights traveling through the fog. And so that's a heterogeneous mixture. So definitely sand and water. That I would call suspension, and I would say that it's a heterogeneous mixture. All right, so between these two extremes, homogeneous and heterogeneous, there's an intermediate state called a colloid suspension, or simply colloid. So the colloid is a dispersion of particles throughout the solvent, but the particles are larger than normal solute molecules. So normal solute, this is what would happen. And if I dissolve table salt and water, so I have table salt, I have sodium ions and chloride ions in the water, and I shine a light in it. It goes through and it pops out the other side, but you don't see the beam traveling through the sodium chloride solution because the sodium ion and chloride ions are so small that they don't interact. But if the particles get so large that they start to interact with the light, called the Tyndall effect, then we say, no, this isn't a homogeneous mixture anymore. We would call it, if you can't see the particles with the naked eye, we generally call them colloids. And look at the range there. If you look at the range of the size of the particles, that gives you an idea of what we're talking about here. So generally, colloidal particles are in range of 1 times 10 to the third picometers to 1 times 10 to the sixth picometers. So these are things you're not going to see, but when you shine the light through it, you will see that scattering. So a colloid suspension lacks homogeneity of a true solution. But it's different than just a suspension, because in a true solution, it's all one phase. And a colloid, it may look one phase or it may look a little cloudy, but when you shine a light on it, you will see the beam going through the mixture. And then a suspension, the particles have gotten so large that they will settle out due to gravity, and so they eventually settle out like so. So that's kind of the difference. So that's what they're saying by intermediate. This is a solution, homogeneous mixture. This is a heterogeneous suspension, and in between is a colloid, like milk. Think of milk as a colloid. All right, if I take a really strong beam of light, I can see the beam traveling through the milk. So colloids can be categorized as aerosols. They can be categorized as foams, emulsions, sols, and gels. I kind of speak the language here. Aerosols, a liquid or solid dispersed in a gas. Foams are gas dispersed in liquid or solid, so think shaving cream here. Emulsions, think mayonnaise, liquid dispersed in another liquid. Eggs dispersed in oil. Sols, solids dispersed in liquid or another solid. And then gels, liquid dispersed in a solid. So you've got some kind of solid, maybe, and then you've got these suspended liquids in here. So think of a contact lens, something like that. All right. So the contact lens, the whole thing it's a membrane, but it holds water, and so it allows oxygen to transfer to the cornea to keep it alive, and so it's a liquid suspended in a solid membrane here. If there's no water in that contact, it would dry out and it would be miserable to wear. So think of something like that. All right, some other colloids. Actually, these are ones that I just started talking about. So here they are. Here's some real concrete examples of different colloids. Just trying to see mayonnaise. Yeah, I mean, I think it's funny they don't put milk, just milk on here. But milk could be an example of a liquid type. It's the fatty globules or the calcium ion. Yeah, maybe that's why you can think of it in whole milk. It'd be the fatty globules suspended in the whey, if you want to think of it that way, the liquid part. Here it is. Here's the Tyndall effect. So you can see in this. This is a nice picture that you can see that as you pass the beam of light through. This is your number one test that you have you don't have a solution. If you can see the beam going through, like here, not so much here. So this is more, I don't know if they're trying to show you that's a colloid or a suspension there. It's kind of hard to tell if you can see the particles, although it does look kind of cloudy down here. I mean, there's something dark there, but it could be the background. But this is definitely not a solution. And this is definitely not a solution. But see how there's no light passing through here? That tells me this is a solution. And then they give you the example. As the light comes off the cars or the street lights, if we got so much large water molecules coagulated together that they scatter light, then we definitely have a colloid here. It's not a solution. It's not homogeneous. You can see that and that could be a light thing, but it's not uniform throughout. More importantly, though, for colloids, and the reason why I wanted to bring this up was that the important colloids are those that which the dispersing medium is water, especially in biology, and so. In biology, if you've had some biology like chemistry or biology 150, you definitely have heard hydrophilic and hydrophobic. And that's what we're getting at, right? Contact lenses kind of thing. Hydrophilic, hydrophobic. Hydrophilic means water loving, hydrophobic means water fearing. And it says in the aqueous phase, proteins like hemoglobin folds in such a way to be hydrophilic parts of the molecule. And then other parts react favorably with the water molecules and ion dipole forces and hydrogen bonding formation on the outside surface. So you say, why do I need to know this? When we start looking at complex like a protein or some larger macromolecule, we can see that the molecule itself is large, and if we looked at this, it would scatter light because the protein is fairly large, and it has these hydrophilic sites on it. All of these where it's polar, you're going to have hydrophilic sites, and where it's nonpolar, you're going to have hydrophobic sites. So it plays out in everyday life that, let's look at this next slide, that these hydrophobic colloids will repel each other. They're not, and so hydrophobic colloids would normally not be stable in water. The particles would clump together like droplets of oil in water, okay? But they can be stabilized, however, by adsorption of ions. So normally these two things would clump together, that one and that one, because they're both nonpolar, if you want to think of it that way. And so London dispersion forces would cause these to clump together. They got a lot of surface to them. If they come close to one another, they're going to stick and clump together. But if ions can be attached to the outside of these proteins, now we have an ion interaction, and like charges repel each other, and so these two proteins won't clump together. All right. So that's what's important about colloids and proteins in biology, is that we are going to see that interaction, whether biologics are attracted to one another or repelled by one another. It says materials that collect on the surface are adsorbed. Make sure you know what the word here means. If it's collected on the surface, it's adsorption. Whereas materials that pass through the interior is absorbed. Know those two terms. Know those two terms. Adsorbed, collects on the surface, passes through the interior, absorbed. The absorbed ion, adsorbed, which is on the surface of a are hydrophilic, water-loving, and can interact with water and stabilize the colloid. In addition, it says the adsorption of those ions leaves the colloid particle charged, and the electrostatic repulsion prevents the clumping together. Probably the most important slide about the colloids right there. So then you go, why do I need to know this again? Let me give you a real world example. And I like this. So this is it. This is the greatest real world example I can think of. So how do you wash your clothes? All right. So you have a washer drum, and you put your clothes in here. We'll put a piece of cloth in here. It's got oil on it from your body, and you fill this up full of water, and you add a detergent. All right. So what is a detergent? Well, a detergent looks just like this. In fact, if you look on your detergents, you may even see, especially in shampoos, sodium stearate. So it's an ionic compound, right? You have this part that's negative, and then you have the sodium on. So it is ionic. And what you have is you have a hydrophilic head, a water-loving head, which is this ionic part. And then all of this from chapter 11, you know that this is nonpolar. It's covalently bound. What this sticks to is another similar substance right next to it through London dispersion forces. So you have the polar end of the molecule and you have the nonpolar end of the molecule. So what happens is these nonpolar ends of the detergent are attracted to the oil. And so here's my oil droplet, and then you have all of these long chains, and then coming out the end is the hydrophilic component. So this part here is this part. And so the dirt gets surrounded by the detergent. Again, the nonpolar end is attracted to the dirt because the oil on your clothes is nonpolar. But then out here on the surface, it's all the hydrophilic, the water-loving part, the ions. So the water's in your washing machine. And so, again, these detergents surround the dirt. And then you have the rinse cycle. Let's see. No, you spin that off. All right, you spin that off. And so all of this goes out with the water. And so then what you have is you have your clothes, which now has lost its oil because the detergent has surrounded the dirt, went out with that draining of the water, and then you fill it up with the rinse water. So what the rinse water is to get the excess detergent out that wasn't reacted. You always put in more detergent than there's oil in your clothes. And so then you have a rinse cycle. You spin that out, and now you have your clean clothes. So this is really important in biology. It is a colloid. This is called a micelle, and if you've had biology, you know that that was a micelle. That's a colloid, a micelle. And again, if you would shine light through this, and it was a glass, you would see the beam passing through there because that's a colloid. All right, so this is why it's important. This is why it was so important, and so that's what it looks like. Grease, the micelle. So you grease on your hands, grease, Dawn dishwashing detergent. That's what it does right there. The non-polar end sticks to the grease. The polar end is out here. Eventually it takes off. You get a nice sphere because this doesn't want to come on contact with the water. The protein being non-polar doesn't want to come in contact with the water. They repel each other. Like dissolves like. But when you surround this with this detergent and the outside is water loving, it's going to form a sphere. Here's your micelle. So now it's dissolved in water. When I pour this out, all of it leaves. Whereas here, if I just pour the water out, the grease probably just kind of sticks to the water or sticks to the glass, and now we still have a dirty glass. You know, when you're in the lab and they tell you to clean your glassware, you use Alkanox. And you know the number one test is if you did a good job cleaning your glass is that when you put water in here, it sheets off, it doesn't bead. So if you flip the beaker over and you run water over and it just flows off, no beads, that tells you got a good clean piece of glassware. So that's where we're going with that. So where else do we see this? We see it in, so here's biosalts that, again, the fats that we eat, how do we get those digested? And again, if you look at this, there's the water loving part here, and then we have some non-polar parts here that they're aromatics, and so again, this is what we need. Or sodium glycocholate. Yeah, cholate. I said glycophosphate or something. I didn't glycolate. Glycocolate. All right. So biosalt. So this is how we digest fats, so that we can use them for energy in our bodies. All right. That's where we're going to stop at. That's the end of chapter 13. It's a nice warm up to Chem 180. It should jog your memory of things in Chem 170 like naming, ions, charges on the ions, solubility rules, intermolecular forces, structure is important, and then we apply that to the physical properties of solutions. So I hope you've enjoyed the chapter. I hope that you found it interesting and that it's applicable to some of your other courses that you're taking. It does set you up for organic chemistry coming up. So this is an important chapter definitely for organic chemistry. And I would say Biology 150 if you haven't had it, and definitely cell biology. So we'll stop here, and that finishes up chapter 13. Email me if you have questions.